Okay, so today we're going to be talking about generative adversarial networks. So we're going to start introducing yet another class of generative models. Just as a recap, this is kind of like the high-level story, high-level roadmap for the kind of things we're going to be talking about in this course. The high-level idea when you build a generative model is that you start with some data, and you assume that the data is basically a set of IID samples from some unknown probability distribution that we denote P data. And then you have a model family, which is a set of probability distributions that are parameterized usually by neural networks. And then what you do is you define some kind of notion of similarity between the data distribution and the model distribution, and then you try to optimize over the set of probability distribution in your model family, and you try to find one that is close to the data distribution according to some notion of similarity. And we've seen different ways of basically constructing probability distributions in this set. And we've seen autoregressive models where you have chain rule and you break down basically the generative modeling problem as a sequence of simple prediction problems. We've seen variational autoencoders where we're essentially, again, modeling the density over the data using essentially like a big mixture model. And then the last class of models we've seen is this idea of a normalizing flow model, which is kind of like a variational autoencoder with a special type of decoder, which is just a deterministic invertible transformation, where again we kind of like get these densities through the change of variable rule. But the key thing is that we essentially always try to model the probability assigned by the model to any particular data point. And the reason we do that is that if we can do that, then we can do maximum likelihood training. So if you know how to evaluate probabilities according to the model, then there is a very natural way of training the models, which is basically this idea of minimizing the KL divergence between the data distribution and the model distribution, which, as we know, is equivalent to maximizing likelihoods. And so there's a very natural and very principled way of comparing probability distributions that works very well when you have access to likelihoods. And a lot of this machinery kind of like involves way of setting up models such that you can evaluate likelihoods efficiently. And that's one way of doing things. What we're going to see today is basically a different way of comparing similarity or of measuring similarity between probability distributions. So we're going to kind of change this piece of the story, and we're going to try to compare probability distributions in a different way. And by doing that, we will get a lot of flexibility in terms of defining the model family, because we will not have to essentially, the training objective is not going to be based on maximum likelihood anymore. And so we're going to get more flexibility essentially in terms of defining the generative model itself. So remember that, again, sort of like what we've been doing so far is training models by maximum likelihood. So the idea is that we have access to the density or the probability mass function over each data point. So we can ask the model how likely are you to generate this particular data point, xi in this case. And if we can do that, then we can also try to choose parameters such that we maximize the probability that the model generated the training data set that we have access to, or equivalently, we can choose parameters to try to maximize the average log probability assigned by the model to our training set. And there is good reasons for choosing this kind of learning objective. In particular, it can be shown that this is optimal in a certain sense. And what I mean is that basically, under some assumptions, which are not necessarily true in practice, but under some ideal assumptions, under an ideal setting where you have a sufficiently powerful model and there is some kind of like identifiability condition, not super important, but under some technical conditions, you can prove that basically trying to estimate the parameters of the models but maximizing likelihood, by basically solving this particular optimization problem, is the most efficient way of using the data. So basically, there is going to be other kind of like learning objectives that you can set up that would potentially give you estimates of the true parameters of the model. But among all these various techniques, the maximum likelihood one is the one that converges the fastest, which basically means that given a certain amount of data, this is the best thing you can do. It's the one that will give you the right answer, basically, using the least amount of data. And so that's why using maximum likelihood is a good idea, because in some sense, you're making the best possible use of the data you have access to under some technical conditions. And the other reason that maximum likelihood is a good training objective is that we've seen that it corresponds to a compression problem. So if you can achieve high likelihood on a data set, then it means that you would do reasonably well at compressing the data. And we know that compression is a reasonable kind of like a learning objective, is one of the, in some sense, like if you're able to compress the data, then it means that you can kind of like predict the things that could happen pretty well. And it's a good way of forcing you to understand what the patterns in the data. And so compression is typically a pretty good kind of like learning objective. However, it might not be necessarily what we want. And so what we'll see first is that there are cases in which achieving high likelihood might not necessarily be correlated with, let's say, achieving good sample quality. So if you're thinking about training a generative model over images, for example, it's possible to construct models that would give you high likelihood and terrible samples in terms of quality. And vice versa, it's going to be possible to train models that have very good sample quality, meaning they produce images that are very realistic, but they have terrible likelihoods at the same time. And so, although, training by maximum likelihood has good properties, it might not be necessarily what we want if what you care about is, let's say, generating pretty samples or pretty images. And so that's kind of like going to be some motivation for choosing different sort of training objectives that are not necessarily going to be based on maximum likelihood. So let's see kind of like what does this mean a little bit more rigorously. First, what we know is that if somehow you're able to find the true global optimum of this optimization problem, so if you're really able to find a model distribution that perfectly matches the data distribution, so somehow if you go back to this picture, if you're able to make this distance exactly zero, the KL divergence between the data and the model is truly zero, so you're able to reach the global optimum of this optimization problem, then you are in good shape because, well, you get the best possible likelihood and the samples that you produce are perfect essentially by definition because your model is exactly equal to the data distribution, and so if you sample from the model, it's like sampling from the data, and so that's as good as it gets. But what we're going to see is that as long as the match is not perfect, as long as there is a little bit of a gap, which in practice is always going to be the case, then being close in KL divergence or equivalently doing well with respect to likelihood doesn't necessarily mean that you are achieving good sample quality, right? But somehow if you're really able to get the true global optimum, then you're good. But for imperfect models, achieving high likelihoods does not necessarily mean that you achieve good sample quality, and vice versa.
Is there like a phase change almost region around the optimum where suddenly you begin getting the best results, and up until that you're getting lackluster but decent results?
So we'll see that is unfortunately not really. And here is an example where you can get very good likelihoods, but very bad samples. And so to do that, you can basically imagine a situation like this, where you come up with this model, which is a mixture of two distributions. It's a mixture of the true data distribution and some garbage, pure noise distribution. And so the sampling process is something like this here. You flip a coin, and then with 99% probability, you generate noise, you generate garbage, and with 1% probability, you generate a true sample from the data distribution. Of course, in practice, you cannot really do this, but this is just to show that there exist models that achieve very good likelihoods, as we'll see, but very good sample quality. And what I mean, the sample quality is bad because 99% of the time, you are generating pure garbage. And only 1% of the time, you're generating good samples. And what we'll see is that even though this model is generating very best samples, it actually achieves very good likelihoods. And to see that is actually a relatively simple kind of derivation. When you evaluate the probability of a data point X, according to this model, you get a sum of two terms. It's the true probability under the data distribution, and it's the probability under the noise distribution. And even though the noise distribution could be really bad, the probability is at least as good as there's a 1% probability of sampling from the data. And so the probability assigned to this data point is at least as large as, this is a sum of two non-negative quantities. And so this log is at least as large as the log of that little contribution that comes from the data distribution. And because we're taking logs, the log of 1% times p data is equal to the log of p data minus this log of 100. So somehow, basically what we're seeing here is that the log probability assigned by this model to a data point is the best log probability you can get, the one that you get according to the true data distribution, shifted down by some constant. And in particular, what this means is that if you take an expectation of this with respect to the data distribution, so you want to see what is the average log likelihood that this model achieves, if you take an expectation of the left-hand side, you take an expectation of the right-hand side, you get that on average, this model performs reasonably well. In the sense that it performs as well as what you would get if you were to use the true data distribution as a model, shifted by some constant. And we know, because KL divergence is non-negative, that somehow this is the best you can do. The average log likelihood for any model cannot be possibly better than the log likelihood that you would get if you were to use the true data distribution to evaluate likelihoods of samples produced by the data distribution. All right, this is just, the KL divergence is non-negative, which just if you just move the log on the other side, is just saying that the data distribution, if the data is coming from the data distribution, the best model of the world you can possibly have is the one that produced the data. It's the data distribution. And no matter how clever you are in choosing data, you cannot possibly do better than using the true model that produced the data. And so you can see that kind of like this, performance that we get is kind of like bounded above by this basically entropy of the data distribution, and below by the same thing shifted by a little bit. And what I argue is that that constant doesn't matter too much, because if you think about it, as we increase the number of dimensions, so as we go in higher and higher dimensions, the likelihood, so this piece will basically scale linearly in the number of dimensions, while the constant is fixed. It doesn't depend on how many variables you're modeling. And the intuition is that if you, for example, you look at you factorize, oh, this is a mistake, this is meant to be p data, sorry, there's a typo here. But basically, if you factorize the true data distribution according to the chain rule, you can kind of see that this term here, the log p data, scales linearly in the number of variables that you have. While the second piece does not depend on the number of variables. And so you can kind of see that in high dimensions, this model is basically doing as well as you could hope to do. the likelihood of this model, which is producing garbage 99% of the time, is pretty close to the best you can possibly achieve. And so I think back to your question, it means that there is a model that is very close to the optimal one and is still producing very, very bad results, especially in high dimensions. Yeah.
It's tangential, but like, doesn't this also motivate us training models not only on like good images, but like assigning bad probabilities to like bad images or noise images, and I can like very easily generate bad images.
Yeah, that's a good question. Yeah, to what extent could you use, let's say, bad data and somehow train the models that way? It's not obvious how you would do it with the maximum likelihood, but using GANs, which is what we're going to talk about today, it's actually pretty straightforward to incorporate negative data. So if you know that there are certain things that are clearly not possible or things you don't like, then it's pretty straightforward to kind of like incorporate that sort of like negative data augmentation into your training objective. For example, yeah, like if you're training on images and you apply some kind of like jigsaw operator where you kind of like produce a puzzle and then you move the pieces around, you get an image that kind of has the right local texture, but it's not something you want. And you can incorporate that kind of data augmentation essentially, or negative data augmentation to improve the training. So that applies generally. It's a little bit trickier to do with likelihood-based models, but yeah, that's a good idea.
Could you use like some type of ensemble to model the noise separately? Like I know you can do it for like standard supervised learning. I'm not sure if you can also do it in a generation setting where you just like model noise separately, take it out, and then only have true data that you're modeling. So
you're saying it kind of have a mixture that is trying to, like, where would the noise come to try to filter it out, or?
Yeah, like typically if you train several ensembles,
yeah,
one of the part that they pick up is from the true distribution, and then the noise part is picked up separately. But if you average a lot of them, then you only reinforce the common signals, and then the noise components cancel each other out. I'm just curious if you could do something similar.
I think in general, like we don't assume, I guess we're not in the setting where we are assuming that there is even noise in the training data. So, or I think what we were talking about is a setting where you know what you don't want and you want to kind of like take advantage of that, but you don't have to figure out what is noise and what is not because you kind of already know. And here we're in the setting where we're assuming the data is clean. The data is really just a bunch of samples from the data distribution. So you do want to use everything you have access to, and there is no need to filter the noise. This is just a model of the world that is kind of like made up, but it's kind of illustrating the point that optimizing likelihoods might not give you good sample quality, because at least conceptually it's possible that by optimizing likelihood, you end up with a model like this, which would produce garbage 99% of the time, but gives you high likelihoods. Right? And so there is that potential issue. And conversely, it's possible to get models that produce great samples and very bad log likelihoods. Anybody have a guess on how you could do that? How would you? Yeah.
Overfitting.
Overfitting. Yeah, that's probably the simplest way to do it. Just memorize the training set. So you build a model that puts all the probability mass uniform, let's say distribution over the training set. And then if you sample from this model, the samples would look great. I mean, they are by definition just training samples. So basically I cannot do better than that. But the test likelihood would be as bad as it gets, because it's going to assign basically zero probability to anything that the model hasn't seen during training. And so again, terrible log likelihood. So again, this is sort of like suggesting that it might be useful to kind of disentangle a little bit sample quality and likelihood. Even though we had some success training models by maximum likelihood, it's not guaranteed that that's always the case, and there might be other training objectives that will give us good results in practice. And so that's sort of like the main motivation behind the kind of like the key idea behind generative adversarial networks. it's a different kind of training objective that will not depend on the likelihood function. And so back to our high-level picture, basically what we're going to do is we're going to change this performance measure here. We're going to change the way we're comparing how good our model is by throwing away KL divergence, which is what we've been doing so far. And we're going to try some alternative way of comparing two probability distributions that will not rely on likelihood. Yeah.
So in the third case, how is the samples looking exactly like the training set grade samples? Like, are we, because like, how do you define grade samples?
Yeah, it's a good question. What is a great sample? Maybe you want the samples to have diversity, in which case maybe this wouldn't be. But if you think about images, like if you were to look at them, they would look, perfect. They would have the right structure. They would be good, except that there is not maybe enough variety because you're not really generating anything new. But presumably it would be, in terms of just quality of the individual samples, this should be good, basically. Yeah, for each individual sample, the quality would be good. Great, so let's see how we can do it. And so the basic idea is that we're going to think about exactly that problem of deciding, whether or not two distributions are similar by looking at the kind of samples you get if you were to sample from one or the other. And so you can imagine this setting where I give you a bunch of samples that are samples from some distribution P, and I give you a bunch of samples that are coming from some distribution Q. And what we can try to do is we can try to figure out if there is a way to tell whether or not P, this distribution that we used to generate the first batch, this group of samples, is actually the same as the distribution that we used to generate the right group of samples. If you can do that, then that could be a good way of kind of like comparing probability distributions, because if we don't have a way of telling whether or not the distributions are different, then it probably means that the distributions are close to each other. And so that's basically what we're going to do is we're going to use something called a two-sample test, which is basically a procedure for determining whether or not these two groups of samples, S1 and S2, are coming from the same distribution, are generated by the same probability distribution or not. And so it's an hypothesis testing problem, which you might have seen before in other contexts, where basically there is a null hypothesis, which is the distributions are the same. So P is equal to Q, so the samples in the first group have the same distribution as the samples in the second group. And then there is an alternative hypothesis, which is that the distributions are different. Yeah.
Could you explain one more time why we want to compare the distributions?
Yes, we want to compare the distributions because I guess we will need a training objective. So, we typically use KL divergence to figure out how close our model is to the data. And we kind of said, okay, KL divergence is good, but perhaps not ideal in the sense that you can get pretty close in KL divergence and have terrible samples. And so maybe there is room for choosing different comparisons, different ways of comparing probability distributions that are closer to perceptual quality of the samples and will allow us to do things differently. And that's kind of like the main motivation. So one way to go about it is to say, okay, let's say I have a bunch of samples from P data, say I have a bunch of samples from P theta, how do I compare them? And the most basic thing to do is to say, can I decide whether or not they are different? Because if I cannot figure out if they're different, then it means that I'm close, they're the same. So if I fail at this hypothesis testing problem, or it's very hard to kind of like do well in this task, then it means the distribution are similar. And so I have a pretty good way of, then I have a reasonable way of comparing. Then maybe I'm doing well at my learning problem. And so that's kind of like the intuition.
But isn't there also like the issue of like the randomness of the p-value coming into play? Because like, for example, if you set the p-value at 5%, then just like 5% of times, right? Even if they are the same, you will reject
Right. So the way, and this is getting at, okay, how do you do it? Typically, what you would do is you would come up with a test statistic, which is just a function that you use to compare these two sets. For example, you might try to look at what is the mean of the samples in the first group versus the mean of the samples in the second group. Or you could look at the variance, the sample variance of the samples in S1 versus the sample variance in S2. And presumably, if indeed P is equal to Q, then you would expect the mean of the samples in here to be similar to the means of the samples in here. And you would expect the variances to be similar. So for example, one statistic you could try is to do something like this, where you compute the mean in the first group, you compute the mean in the second group, and then you compare them. And what you could do is you could say, okay, if this statistic is larger than some threshold, then I reject the null hypothesis. Otherwise, I say that H0, so the null hypothesis, is consistent with my observation. And as you were saying, there is always some kind of type 1 and type 2 error, in the sense that T is random, because S1 and S2 are random. And so even when P is equal to Q, it's possible that the means are different just because of randomness. It's not going to be super important to what we're going to do. But yeah, it's a hard problem. It's, even if you had a good statistic, there is still going to be some probability of error. But you could ask the question of, okay, what's the best statistic for determining whether or not to solve this hypothesis testing problem? And you could try to minimize type 1 and type 2 errors. Right? There's going to be false positives, there's going to be false negatives, but you can try to choose a statistic that minimizes these types of errors.
Does it have to be like a differentiable function? Can I have human preference as my test statistic?
We'll see how to come up with this T. This is just kind of handcrafted, and it's not the best one, but it's going to be similar to it's going to be learned, basically. Yeah.
Wait, so here are you trying to distinguish between two different distributions your initial samples coming from, or also two different types of generative models that are making the final output?
It could be both. In practice, one is going to be real data. One is going to be, let's say S1 is going to be samples from the data distribution, and S2 is going to be samples from our model. But it doesn't have to. It could be two models. It could be, this is pretty generic. But the way we're going to actually use it for a generative adversarial network, it's going to be one group of samples are going to be real, one group of samples are going to come from the models, they're going to be fake, and then we're going to use some kind of statistic to try to determine whether or not these two samples are similar. And the key observation here is that at least there is some room for choosing different kind of test statistics, and you can choose some statistics which do not depend on the likelihood of P or Q. For example, you just look at the means, you don't need to know the probability, you don't need to be able to evaluate probabilities under P, you don't need to evaluate probabilities under Q, you can compute this function just based on a bunch of samples.
You mentioned you can just overfit and replicate P data. How would this two-symbol test deal with that? Because it's still going to be the same samples.
Yeah, so the question is, does it solve the overfitting problem? You still have the overfitting problem. Just like even if you do maximum likelihood, you can still have overfitting problem. So this does not directly address the overfitting directly. Although, yeah, you can sometimes at least you can use kind of like validation and other things to see what would be the, we'll see, yeah.
So the test statistic, which is if you choose it to be your constant entropy loss, then it's the same thing as maximizing the K level.
You could, so you could try to choose test statistics that are based on the likelihood of the model, but you don't have to. And so, again, sort of like the setting of generative modeling with two sample tests is one where there's going to be a bunch of samples that are just going to be coming from the data distribution. Recall that that's all we we always assume that somebody's giving us access to a bunch of samples that are coming from the data distribution, and that's our training set. And so that's going to be the first group of samples. Then, just like before, we have a set of models. We have a set of distributions p theta that we're willing to consider. And as long as these distributions are easy to sample from, which is not a terrible requirement because presumably you're going to use the model to generate samples anyways, but as long as you can somehow sample from the model, you can always generate the second set of samples S2, which are just basically samples from the model. And then what you can do is you can try to train. Basically, the high-level idea is going to be, instead of trying to find a model p theta, just going to optimize over this set so that we minimize the KL divergence between these two distributions. We're going to try to find a model that tries to minimize this whatever test statistic that we've decided to use to compare two set of samples. And right, for example, in the previous example, it could be something like try to make sure that the means of the samples that I produce matches the mean of the samples that I had in the training set, which would not be very useful, but that's sort of like the high-level idea. And so the problem is that kind of like finding a good statistic is not easy. For example, if you were to just try to minimize this kind of test statistic here, you would end up with a generative model that produces samples with the same mean as the training set, which is, it's a property that is desirable, but it's not sufficient. Like if you just match the mean, you can still produce very bad samples and fool this kind of test statistic. And that's sort of like the problem, is that in high dimensions, it's very hard to find some good test statistic. And so kind of intuitively, you could say, okay, let's say that you start comparing probability distributions by matching the mean. And so if you compare the means, you would be able to distinguish, let's say that this green Gaussian is different from this red Gaussian. But then you could say, okay, just matching the means is not sufficient. Here are two Gaussians that have the same mean, but different variances. So if you just compare the means, you would not be able to distinguish between those two Gaussians. And then maybe even if you match, let's say, the mean and the variance, you could have different distributions that have the same first moments, or same mean and same variance, like Gaussian and a Laplace density. Same mean, same variances, but different shapes. So kind of like you can kind of get a sense that especially the more dimensions you have, say you're modeling a lot of pixels or a lot of tokens, there is many different ways in which or many different things you could look at when you compare two probability distributions. There's many different features that you could try to kind of compare samples with respect to. And so kind of like handcrafting a test statistic and just say, okay, let's try to train a model based on that is unlikely to work, because you're going to match the test statistic, and then there's going to be other differences that you didn't think about that actually matter in practice. And so what we are going to do is we're going to try to, instead of picking a fixed handcrafted test statistic, we're going to try to learn one to sort of like automatically identify in which ways these two set of samples, the one from the data and the one from the model, they differ from each other. Instead of keeping it fixed and just say, oh, let's compare the mean, we're going to try to learn what makes these two samples different. And how to do that? Any guess? We're going to try to just basically train a classifier, essentially, which in the language of generative adversarial networks is called a discriminator. So we're going to, machine learning, that's exactly what you would do, if you are trying to solve a classification problem, you're trying to figure out what distinguishes the positive class from the negative class. The job of a classifier, for example, a deep neural network, is to identify features that allow you to discriminate and distinguish these two groups of samples. So we're going to use the same kind of idea to figure out what sort of features of the data should we look at to discriminate between the green curve and the red curve, essentially. And so that's basically what we're going to do, is we're going to train a classifier, again, it's called a discriminator in this context, to basically classify. We're going to use a binary classifier, for example, a neural network, to try to distinguish real samples, which are basically the ones from the first set, the one generated by the data distribution, which let's say is label 1, from fake samples, which are the ones generated by p theta, by our model, which we can say, for example, label 0. And we can train a classifier to do that. And as a test statistic, we can use the minus the loss of the classifier. Why do we do this? Well, what happens if the loss of the classifier is high? If, well, let's start. If the loss of the classifier is low, then it means that you're doing a very good job as distinguishing the two. They're very well separated. Your classifier is doing a very good job at distinguishing these two groups of samples. And so they're very different, and so we want the test statistic to be small, to be large, sorry. And if we have a high loss, then the real and the fake samples are hard to distinguish, and so we expect them to be similar. Yeah.
How is this likelihood free though? I'm just a little bit confused because like if we're predicting if you're doing this classification task, the likelihood, the loss is still likely.
Yeah, good question. So you're exactly right. So it's based on the likelihood of the classifier. It's not based on the likelihood of the generative model. So by doing things this way, we're going to use the likelihood, but it's going to be the likelihood of a classifier. And that's much easier because that's just going to be a likelihood over basically a binary variable. And so essentially it doesn't really put any restriction on the kind of neural network you can use, as opposed to the likelihood over x over the input, which requires you to either use autoregressive models or invertible neural networks. It puts a lot of restrictions on the kind of architectures you can use. Here it's just going to be a likelihood over basically a binary random variable, which is the class label. And so all you have to do is you have to have a softmax at the end that maps it to a probability, but then you can do whatever you want with respect to the x. So you can extract whatever features you want of the input x to come up with a good classifier, and there is really no restriction on the kind of architecture.
It's much easier to optimize.
Yeah. And so the goal of this classifier, the way we're going to train this classifier, is to maximize the two-sample test statistic to basically try to figure out what kind of statistic basically can maximally distinguish basically between the data and the model, which is the same as minimizing the classification loss. So we're going to train the classifier the usual way to minimize the loss, because that's also what gives us the most power to basically distinguish these two distributions, these two set of samples. Yeah.
To clarify, like before you were talking about what statistics should we use in order to figure out if they're different. In this case, am I understanding correctly that we don't end up really even thinking about what that statistic necessarily is? We're just doing the classification in order to figure out if it exceeds or...
It's going to be actually a statistic. So this is the actual statistic. It could be something like this. So it's actually more like a family of statistics, which are all the ones that you can get as you change. You have a classifier, and then you can imagine changing the parameters of the classifier. And then you can think about, if you were to try to find a classifier that maximizes this objective function, which is just minimizing cross entropy, which you approximate based on data because you only have samples from p data and you only have samples from the model, you end up with something that looks like this, which is going to be the statistic. Right? Remember before we were just taking the mean of x in S1 and the mean of x of the samples in S2. Now we don't just look at the means, now we look at what the classifier says on these two samples. And that's what we're gonna use. And basically, as we discussed before, like if the law, this is the negative loss of the classifier because I'm maximizing. And so if this quantity is large, then it means that you're doing a good job at separating them, and it means that they are different. And if the loss is, if this quantity is low, then it means that you're very confused. You're not doing a good job at distinguishing them, which supports the idea that probably they are similar. It's not hard, it's hard to distinguish.
Can you just clarify the notation?
Yeah, so what we have here is the setting is the one we had before, where we're saying, we're gonna use as a statistic, we're gonna use a classifier, which we're gonna denote as D5 because it's gonna be trainable. It's gonna be another neural network that we're gonna train. And they're gonna train this neural network to try to distinguish between the samples in S1 and the samples in S2, where the samples in S1 are it's just a sample from a group of IID samples from the data distribution, and S2 is just a group of samples from the model distribution, p theta. And if you maximize this objective function over the classifier, you are basically trying to do as well as you can at this, you're basically just training the classifier the usual way by minimizing cross entropy. And this is going to be our statistic in the sense that the loss of the classifier will tell us how similar basically these two groups of samples are. And basically, yeah, the discriminator, the phi, is performing binary classification with the cross entropy objective. And you can kind of see that you are going to do well here, what you're supposed to do is you're supposed to assign probability 1 to all the samples that come from p data, and you're supposed to assign probability 0 to all the samples that come from the model, if you want to maximize that quantity. Which, again, is basically what you would do if you were to train a classifier, distinguish the two groups of samples, and that's just like the negative cross entropy. So for now, p theta is just fixed. It's the model distribution. The data distribution, as usual, is fixed. You just have a bunch of samples from it. That's S1. And what we're saying is we're going to try to optimize the classifier to do as well as it can at this task of distinguishing between real samples and fake samples. Because the loss of the classifier will basically tell us how similar the samples that come from the model are to samples that come from the data. Yeah.
Could you please explain again how the loss is telling us if it's what we want?
Yeah. So imagine, do I have it here? Yeah. So imagine that somehow Imagine that the two distributions are the same. So p theta is the same as p data. Then these two samples would come from the same distribution. So the classifier basically cannot do better than chance, because you're literally just taking two groups of samples that come from the same distribution, and then there is no way to distinguish them because they're actually coming from the same distribution. So you cannot do better than chance, and so you would have a high loss. On the other hand, if the samples were very different, the classifier would do a pretty good job of separating them, and then in which case the loss would be small. And so based on that, we can come up with a statistic that would basically say, based on the loss of the classifier, we're going to decide whether or not the samples are similar or not. So to the extent that you can separate them well using a classifier, then we say that they are different. If somehow they are kind of like all overlapping and there is no way of coming up with a good decision boundary, then we're saying, okay, then probably the two samples are similar.
Why do we need the first two? Assuming our discriminator is, even if it's not optimal, we can just set that to be 1.
You need the first term because I guess you do need to contrast it to something. Otherwise, it would be trivial to, like, as you, it's just the usual, like, maybe I misunderstood. Like, if you have a classification problem, you do need the two data from the two classes. Otherwise, there's not really much to learn.
If my model, my generative model, it should just learn to fool the discriminator, right? So it should, like, it can only control samples from PK.
Oh, yeah.
It has nothing to do with it.
Yeah. Okay. You're already one step ahead. You're already thinking about optimizing with respect to theta, which we're not doing here right now. Yeah, but for now, we're just optimizing phi, and that depends on both, clearly. You are right. When you optimize with respect to theta, you only care about the second term, and indeed, the gradients will only involve that term. Yeah.
Could you please go with the notation again?
Yeah, so the notation here is saying, recall that we have a group of samples S1 that are coming from P data. This is your training set, or a mini batch of samples from P data. And then we have another group of samples S2 that are coming from a model distribution P theta. And then we have some kind of objective function here that depends on the model and the discriminator. And what we're saying is that the discriminator is going to try to optimize this quantity, which depends on the model and the discriminator, and it's going to try to maximize it. And that's equivalent to basically trying to do as well as it can at distinguishing real samples from fake samples, which are coming from P theta. The reason we have this V is that we're going to also try to then optimize this function with respect to theta because we want to train the generative model. And so what will show up later is basically a mini-max optimization problem where we're going to optimize this V both with respect to theta and with respect to phi. And so there's going to be a competing game where the discriminator is trying to optimize this V quantity, it's trying to maximize this V quantity, and the model is going to try to minimize that quantity because the model is, we're trying to change P theta to fool the discriminator or try to make the classification problem as hard as possible. So later there will be an outer minimization with respect to theta, and that's how we train the model. Cool. And it turns out that the optimal discriminator actually has this form, which kind of like makes sense. This is just if you just use Bayes' rule and you compute what is the true conditional probability of a point X belonging to the positive class, which in this case is, let's say, the data distribution, real samples. Well, the true conditional distribution is basically the probability that that point was generated by the data distribution divided by the total probability that that point was actually generated by either the model or the real data distribution. And so in particular, you can see that if X is only possible according to the data distribution, then the model should assign, the optimal discriminator would assign 1. Because you have basically 1 over 1 plus 0, and then it would be 1. While, for example, if the two models are the same, so if a point is equally likely to come from P data or P theta, then this quantity should be 1/2, which kind of like makes sense because if X is equally likely under P theta and the P data, then the best you can do is to say 1/2 probability. While if a point is much more likely to have come from P data, because this ratio is large, then the classifier should assign high probability to that point. And if a point is very unlikely to have come from P data, because the numerator is small, then the classifier should assign low probability to that point.
So in this case, like the most confused the discriminator can be is if P theta equals P data, which seems like we're going back to the objective we were trying to get away from, which is that you don't want to minimize the KL divergence between the two distributions. So like, I guess, how do we escape that problem?
So we don't, because it's true that the KL divergence is going to be minimized when the two distributions are the same. and that's the global optimum of the KL divergence. So whatever we do, we're still going to go towards that global optimum. In practice, you cannot actually reach it. And so really what matters is that if you have an imperfect model, so you cannot really achieve this, the KL divergence will take some non-zero value. This quantity might take some other non-zero value. And the argument could be that perhaps among the suboptimal models, you should prefer one that cannot fool a discriminator, as opposed to one that gives you high compression, because maybe that's more aligned to what you care about.
Can I have a discriminator that's just a generative model with a softmax over the final PFX? Does it need to be like a binary? Like I can have another generative model that I trained with, let's say, normal care divergence, and I use that as my discriminator when I'm training a separate model.
So you're saying, can you use a likelihood-based model to do the discriminator? Yeah, you can. There are actually variants of ways of training generative models that are kind of along those lines. We're going to talk a little bit about that when we talk about noise contrastive estimation. I think it's going to be pretty similar to what you're suggesting. So yeah, if you have access to a likelihood or part of the likelihood, then you can sort of like take advantage of it and try to design, but then that defeats the purpose. As what we'll see is that the main advantage of this is that you don't have to have access to a likelihood. The only thing you need is to be able to sample from the model efficiently, which means that you can use essentially an arbitrary neural network to define the generative process, which is a big advantage of this kind of procedure. Yeah, and so as a sanity check, you can kind of see that if p theta is equal to p theta, then this quantity is going to be 1/2 for every x, which basically means that the best you can do, the classifier will output 0.5 for every x, which is indeed the best you can do. If the distributions are the same, you cannot possibly do better than chance. So this is when the classifier is maximally confused, basically. Okay, so now how do we get the next step? How do we use, now that we've decided that that's going to be our notion of the way we're going to compare how similar basically p data is to p theta. Now we can define a learning objective where we try to optimize p theta to basically fool the discriminator. And so it's going to be a kind of like a game. It's going to be a minimax optimization problem between a generator, which is just your generative model, and this discriminator, this classifier. And the generator is just going to be a generative model, typically, that basically looks like a flow model, in the sense that you start with a latent variable z, and then you map it to a sample through some deterministic mapping, which is parameterized by a neural network, and we're going to call it g theta. And so the sampling procedure is the same as a flow model. You sample z from a simple prior, for example, a Gaussian, and then you transform it through this neural network. And crucially, this is similar to a flow, but the mapping does not need to be invertible. It can be an arbitrary neural network. It's an arbitrary sampler. You start with some random vector and you transform it into a sample. No restrictions on what G is.
Also, if not necessarily if you have the same dimensions, right? Z could have...
Exactly, it doesn't need to have the same dimensions, no restrictions basically on what G is. Yeah?
We can just use any generative model here, right? Like VAE.
You could use any generative model, yeah. But the advantage, the typical, we'll see that it's actually convenient. Well, to train it, it would be good if you can sort of like backprop through the generative process. But to some extent, you can indeed use other generative models. But the advantage is that basically you don't have any restrictions on this neural network, right? So we don't have to, there is going to be some distribution over the outputs of this neural network, but we're not ever going to compute it. So unlike autoregressive models or flow models or VAE, where we were always very worried about being able to compute, given an X, what was the likelihood that my model produces that particular X? For these kind of models, we don't even care, because we're going to use 2 sample tests to compare, to train them. And so we don't need to be able to evaluate likelihoods. And so we don't have any restriction, basically, on what this sampling procedure does. It can essentially be anything. And what we do then is we're going to train this generator to do the opposite, basically, of the discriminator. The generator is going to try to change this mapping, which implicitly also changes the kind of samples it produces, to try to minimize this statistic that we were using in support of the fact that of this null hypothesis that says the data is equal to the distribution of samples that I get by using this model. And so the end result is this. You have this minimax optimization problem where the function v is the same. It's this basically the loss of the negative loss of the classifier. And then these 2 players in the game, the generator and the discriminator, they have opposing objectives. The discriminator is going to try to maximize this, which again, this is the same as what we had before. This is just saying classifier, the discriminator is trying to do as well as it can to distinguish samples coming from the data, 2 samples coming from this generative model, from this generator. And the generator is going to do the opposite. It's going to try to minimize this objective function, which basically means the generator is trying to confuse the classifier as much as it can. It's going to try to produce samples such that the best classifier you can throw at that, when you compare them to the data distribution, the best classifier is going to perform poorly, which supports the fact that if a classifier cannot distinguish the samples I produce from the samples that are in the data set, then I probably have pretty good samples. And that's sort of like the training objective that we're going to use for training this class of generative models. And so now it turns out that this is related to a notion of similarity between probability distributions. We know that what the optimal discriminator is that it's just a density ratio, p data over p data plus p model, basically. And we know that basically, the optimal discriminator is going to depend on what the generator does, and we can evaluate the value of this objective function when basically the second player, the discriminator, is picking the best possible thing it can do given what the generator is doing. And because we know what that looks like, right? We know that when the discriminator is optimal, the discriminator is just going to give us these density ratios, p data over p data plus p model. So we can plug it into this expression and we get this sort of equation. So this is the optimal loss that you get by choosing. So whenever you choose a generator G, if the classifier if we pick the best classifier given that G and given the data distribution, this is the value of that objective function. This kind of looks like a KL divergence. Like it's an expectation of a log of some density ratios. Remember, KL divergence is expectation of under P of log P over Q, right? This kind of has the flavor. Now the denominators here are not probability distributions. They are not normalized. You have to divide by 2 if you want to get something that integrates to 1. But you can basically just divide by 2 here, and then subtract off that logarithm of 4 that you just added in those denominators. And now this is really just two KL divergences. You can see that this is the KL divergence between the data and a mixture of data and model. And this is KL divergence between model and a mixture, the same thing, mixture of data and model. And then it's shifted by this log4, which is just because I added these 2 here and here, and so you need a log4 there to make it equal. And so what this is saying is that this objective, as a function of the generator, is equal to this sum of KL divergences, which actually has a name. It's called the Jensen-Shannon divergence between the data distribution and the model distribution. So this thing is essentially 2 times this quantity, called the Jensen-Shannon divergence, and which is also known as symmetric KL divergence. Like if you look at that expression, it's basically if you want to compute this Jensen-Shannon divergence between P and Q, you basically do the KL divergence between P and a mixture of half P and half Q, and then you do the reverse. KL divergence between Q and a mixture of P and Q. And this has nice properties. We know KL divergence is non-negative. Sum of 2 KL divergences also has to be non-negative. What is the global optimum of this? Like when can it be 0? Yeah, so it also has the nice property that the global optimum can be achieved if and only if basically the distributions are the same. It's symmetric, which is nice. Remember, KL divergence was not symmetric. The KL PQ is not the same as KL QP. This is symmetrized basically by definition. And it also has triangular inequality, but not super important. And so what this means is that if somehow you can optimize this quantity here as a function of g, so if you minimize this v as a function of g, which is what you do here on the outside, you will basically choose a model distribution that matches the data distribution exactly. So the global optimum is the same as what you would get with KL divergence, and you would get kind of like that optimal loss. So the summary is that basically, as a recap, what we're doing is we're changing the way we're comparing the data distribution and the model distribution. And we choose this similarity based on a 2-sample test statistic, and the statistic is obtained by optimizing a classifier. And under ideal conditions, so that the classifier can basically be optimal, which in practice is not going to be, because if you use a neural network, it might not be able to learn that density ratio. But under ideal conditions, this basically corresponds to not using KL divergence here, and instead using this Jensen-Shannon divergence to compare the data to the model. And the pros is that to evaluate the loss and optimize it, you only need samples from p theta. You don't need to evaluate likelihoods, which is great because that means you don't have restrictions on autoregressive, normalizing things, normalizing flows. You don't have to worry about it. Lots of flexibility in choosing the architecture for the generator. Basically, it just has to define a valid sampling procedure, which is essentially always the case. If you feed in random noise into a neural network, you get a sampling procedure, a valid sampling procedure. That's really all you need. And it's fast sampling because you can generate a sample in a single pass through the generator. So it's not like autoregressive models, one variable at a time. Everything is generated in a single pass. The con is that it's very difficult to actually train in practice because you have this minimax sort of optimization problem. And so in practice, what you would have to do is you would have to do something like this. You would have to, let's say, start with a mini batch of training examples. And then you get a sample of noise vectors from the prior of the generator. And then you pass them through, you pass these noise vectors through G to generate M fake samples. And then you basically have these 2 mini batches. You have M real data points and M fake data points, which is what you get by passing ZI through the generator. And then what you do is you try to optimize your classifier, your discriminator, to maximize that objective. So the classifier is, which is just the usual training of a classifier. Just try to take a, you take a step in a gradient ascent, in this case, step on that objective function to try to improve this optimization objective to do better, basically, at classifying, distinguishing real data from fake data. And kind of like as it was mentioned before, then the generator is also looking at the same objective function, but it has an opposite objective. The generator is trying to minimize that objective function. You can still do gradient descent, and what you do is you compute the gradient of this quantity with respect to theta, which are the generator parameters. And the first term does not depend on theta, that's just the data. So you cannot change what the data looks like, but what you can do is you can try to adjust the parameters of G, so the parameters of the generator, so that the samples that you produce by passing random noise through G kind of look like the real data as measured by this discriminator d phi, which is what you get by taking this kind of gradient descent step on that objective.
For that, like second, the gradient descent step, do we use the updated phi or the previous phi?
Yeah, so it's unfortunately very tricky to train this, and this is not guaranteed to converge. And it can be, in practice, you would use the new phi, and you would keep going and trying to kind of playing this game where each player is trying to play a little bit better and hope that it converges. You repeat this and hope that something good happens. And here is a kind of like a visualization of what happens if you do this. So what's happening here is you can imagine there is a bunch of z vectors that are then mapped by G to different x locations. So here z and x are just one-dimensional. And that is giving us a distribution, which is this green curve. So you see that most of the samples from the generator end up here. And then there is a data distribution, which is just this red curve. That's fixed. It is whatever it is. And then let's say you start with a discriminator, which is not very good, and it's this wiggly kind of blue line here. Now, given that you have a bunch of red samples and you have a bunch of green samples, so real samples and fake ones coming from the current generator, what you would do is you would try to come up with a good classifier. And the better classifier that you get after you update the discriminator is this blue curve. So as you can see, if x's are coming from this left side, then they are probably coming from the real data distribution. Like, there is no chance they come from the generator, because the generator has very low probability here. The data is pretty high, and so the discriminator should say samples around here should have high probability of being real. Samples around here should have high probability of being fake or low probability of being real. And then here in between, it's unclear, and then you just decrease the probability as you move towards the right. So that's what happens when you optimize phi. You basically come up with a better discriminator. Once you have the better discriminator, you can try to update the generator to fool this discriminator. And so what would happen is you would change these arrows here, which are basically the G, which is telling you how you map the random noise from the prior, the Z, to x's that you like. And in particular, if you're trying to fool this discriminator, you're going to try to shift probability mass to the left. And so you might end up with a new generator that looks like this, and that confuses the discriminator more. Because you can see it's overlapping more with the red curve, and the discriminator is going to have a hard time trying to distinguish these two samples. And then you keep going until you reach, hopefully, this kind of convergence where the discriminator, where the generator matches the data distribution, so the green and the red curves are overlapping, they're identical, and the discriminator is maximally confused, and it's producing 1/2 everywhere because it cannot do better than chance at that point.
So
terms of actual implementation, I guess this would not look like a nested loop. This is actually like a single for loop in which you are doing alternate updates.
Yes. Yeah. And so in the as part of what you need to do, I mean, the job of the discriminator is to basically look at a bunch of samples like these two, and you need to decide, which one is real and which one is fake, essentially. And so, which one do you think is real and which one is fake? It's actually both are fake. Yeah. So yeah, and these kind of technologies this improved a lot over the years. Like you can see from 2014 all the way to 2018, and there are even better improvements now. Very successful in a lot of tasks, but it's very challenging in practice to get them to work because of the unstable optimization. Just a random Gaussian noise, see. There's no caption here, yeah. It's just random noise, and then you pass them through a neural network that turns them into images. Yeah. And there are several problems with GANs. The first one is unstable optimization, kind of like because you have this min-max objective, it's very tricky to train them. It's very hard to even know when to stop because it's no longer like likelihood, and you can see it going down, and at some point you can just stop when or up, let's say, you're maximizing likelihood. You see it goes up, and at some point you see it's not improving anymore. You can stop. Here is no longer the case that you know when to stop, basically, and it can have this problem called mode collapse, which we'll see basically. While KL divergence is mode covering, we'll try to put probability mass everywhere because otherwise you get a huge penalty. If something is possible under P data, but you put 0 probability, then you have infinite penalty. These GAN tend to be much more mode seeking, and so they might just focus on a few types of data points and completely stop generating other kinds of data points that are present in a training set. And so in practice, you need a lot of tricks to train these models, and I'm going to point you to some reference for how this, where you can see some of them. I mean, in theory, under some very unrealistic assumptions, that kind of procedure where you do updates on the discriminator and the generator, or at every step, sort of like you find the optimal discriminator, is supposed to work. In practice, it doesn't. In practice, what you see is that the loss keeps oscillating during training. So it might look something like this, where you have the generator loss, which is the green one, the discriminator loss, and the two types of samples, the real and the fake ones. You can see like it kind of keeps oscillating because you're not reaching kind of like it doesn't converge basically through this gradient procedure. And there is no robust stopping criteria. You don't know when should you stop. You don't really know. The only thing you can do is you look at the samples and kind of like see, okay, it's doing something meaningful, and then you just stop. But it's very hard to come up with a principled way of deciding when to stop the training. And so the other problem is that you have mode collapse, which is this problem that, again, the generator is basically collapsing on a few types of samples, and it doesn't generate the other ones. And you can see an example here where kind of like, if you look at the samples, it really likes this type of data points, and it keeps generating it over and over. And you can see kind of like a more toy example that gives you a sense of what's going on. Like imagine the data distribution is just kind of like a mixture of a bunch of Gaussians, whether in 2D, and they're kind of like lying on this circle. And then what happens is that as you train your generator, it kind of like keeps moving around. So maybe at some point it produces one of the modes, and then the discriminator is doing a good job at distinguishing what it does from the real data. Then the generator is moving the probability mass on a different mode, and it keeps moving around, but it never actually covers all of them at the same time.
To make the target distribution become, not as this, have super rows and then trick the our GAN to fit into one mode?
Yeah, so there's all kinds of tricks that you have to use, and here is another example on MNIST where you can see how it's kind of like collapsing on generating one particular digit, and it kind of like stops learning. And there's this great blog post, GAN hacks, where you can see all sort of hacks that you can use to get GANs to work in practice. And there is all kinds of techniques, including noise and various tricks that you can look up on the website. Unfortunately, it's all very empirical. There is nothing that is guaranteed to work, and you kind of have to try. And there are better architectures, there are tricks that sometimes works and sometimes don't. But I would say the fact that these models are so hard to train is why they are no longer kind of state of the art, and people have kind of like largely given up on GANs, and people are using diffusion models instead because they are much easier to train, and they have like a clean loss that you can evaluate during training, and you know how to stop, and there is no instability. It's just a single optimization problem that you have to do. And I would say this is the main reason kind of GANs are no longer so much in fashion anymore. But people are still using them, and it's a powerful idea and it might come back. But I think that's the main drawback. Very, very hard to train.
If we go back to the loss of with respect to the generative function, it seems like the generative model never really sees the actual data. It seems like it's being trained in a very, signal from this discriminator. So it's like very less signal being given to it.
Yeah, so the discriminator is seeing the data, and then the generator is kind of learning from what the discriminator has learned about the data, essentially.
It's like a very narrow signal.
It's a very narrow signal, yeah. And that's why you also keep moving around, because then depending on what kind of features the discriminator is looking for, you might kind of try to catch up with those, but then those keep changing, and then you never really converge to anything.
Can you combine GAN with the standard generative model and hope the best?
Yeah. In fact, there is even recent papers at ICML this year where they were taking a diffusion model, but then they had a clever way of incorporating basically a discriminator to improve performance. And often, if you can throw in maybe a little bit of a discriminator to kind of compare samples in a meaningful way, that often helps. So that's why we're still talking about this idea, because it's actually powerful and you can use it in combination with other existing models. And it's still valuable for other things. Yeah.
Would it be a good idea to initialize the generative model here with a pre-trained VAE, or would you prefer to train it from scratch when you have enough data? What is the...
People usually train it from scratch. Yeah. Okay, and I think we're pretty much at the end. But this I think was the first generative model generated art. It was auctioned at Christie's a few years ago. This is a painting kind of generated by a GAN, one of the best one at that time. I think it was expected to sell for something in that range, and I think it went for almost $500,000. So yeah. Oh yeah. It was, but it was I guess a novelty kind of thing. So yeah, cool. I think that's it.